Okay, good morning everyone. So
Morning.
today we'll start with our next module, this curve tracing. Okay. So before going to the actual part of this, I'll just give you one example and see what you can think over it, and it will also give you some idea about what we are going to do in this complete module. Not module, just some part of the module number 2. Okay. So I'm writing an equation y is equal to 1 upon 1 plus x square. And the question is graph the given equation. Yes, what you can say about this? We'll have some small discussion to make you understand what we are going to do. So please speak up about this. If I want to graph this, what can we do?
Sir, can we integrate it?
What will happen if we integrate this?
We will get some. We will get some terms which we can draw the graph of.
We will substitute x.
Any
We'll put
university?
some x
Yes, sir.
find the, to find the corresponding values of y, and we'll plot it.
So if there is a straight line, then you can actually put the values and get some other value and plot it. I mean, straight line, we know that the equation is like ax plus by equal to c. In this case, if you give the value of x, we get y. Okay, and if I get any 2 points in a plane, I can draw a straight line which is joining them. But this is not a line. Okay, so it can be anything: parabola, hyperbola, neither parabola nor hyperbola, ellipse, whatever. We don't know what it will be. So, taking some 2 to 3 points, we cannot guess in this case because it's not a straight line. So, we will have to go beyond putting some value of x, getting values of y. We'll have to make some concrete observation which will help me draw the graph. So, what do you think those points can be? Okay, let's start with, does this curve pass through origin? First question. How will you check that? Does it pass
The
through
value of
origin?
x.
Someone said it. What is saying? Value of x.
It is not passing from origin.
How can we conclude that?
The putting value of x, we get y as 1.
1. So if you put x as 0, the value of y is becoming 1. So it doesn't pass through origin. So if it has to pass through origin, 0 comma 0 must satisfy the equation. Okay. So this is not satisfying the equation, and that's why it is not passing through origin. So does it intersect x-axis or y-axis?
So it intersects y-axis.
It intersects y-axis. So if we put x equal to 0, we get y equal to 1. We get y is equal to 1. So this point is here, 0, comma 1. Through this point, my curve is passing. Can you tell anything about the tangent at this point to this curve? how can we make some conclusion about a tangent there? Do you have any tool that you have studied till now in mathematics which can tell you what will happen to the tangent to the curve at differentiating? Exactly. So what
and
is dy
to 0.
by dx is equal to minus 1 on 1 plus x square whole square into 2x, right? So if I take this at the point 0 comma 1, what is the value on the right hand side? The answer is 0. What can you say if dy by dx is 0 at that point?
Slope of tangent is 0.
So slope of tangent is 0. It means that the tangent is parallel
Parallel
to
to x.
x-axis. Exactly. So at this point, tangent is like this, right? So the curve must go like this, or it must go like this. Okay. So if it is like this, then and then only this horizontal line will be tangent. Am I right? Now, for any value of x, can mod of y be greater than 1? Is it possible?
No, sir.
No, sir.
So above y equal to 1, there is no curve. I mean, the curve cannot go beyond this. So the curve has to be like this. Okay. So y cannot be greater than 1. Is it possible? The answer is no. So it doesn't go above. So lower one is there. Now, can you make some conclusion what happens to y when x tends to infinity?
Y may become 0.
Y will become 0.
It becomes 0, sir.
So
It
as
tends to 0.
x goes to minus infinity, the value of y will go near and near to 0, right? And as like this, even if x goes to positive infinity, still the value of y becomes 0. Next thing, uh, can you say that, I mean, is this possible mod of y less than 0? Can y be less than 0 for any value of x?
No, sir.
No,
No,
sir.
sir.
No, sir.
So the curve doesn't exist above this curve, above this y equal to 1. Even it doesn't exist below this x-axis. It is always between these two. Moreover, as x tends to infinity, the value of y is becoming 0. And as x tends to plus infinity, still the value of y is becoming 0. And as it comes near to x equal to 0, the value of y is becoming 1. So this kind of curve we have. Okay. So whichever equation consists of x and y, okay, such type of equations are called Cartesian curve. Cartesian equation. Okay. So we will be studying three types of equations. The first one, Cartesian equation, in which many tools are already known to us. We just need to summarize those and use it in a systematic manner to draw or sketch any of the curve. The next curve that we'll be studying is the polar, that I told you while we were studying orthogonal trajectories. So we'll again see that. And the third one which we'll be studying is parametric. Just to give you a rough idea what we mean by parametric is, in your 12th standard, what you have done is you have written x is equal to 80 square, y is equal to 280. What is it? Anyone?
So parametric equation of parabola.
Yes, exactly. So you get x and y in terms of one variable t. So as you change the values of t, you will get different points, but on the parabola. So such type of equations are called the parametric equation. So in this chapter, what we are going to learn is we'll learn how to trace a Cartesian curve, how to trace a polar curve, and how to trace parametric curve.
Sir, can you please explain once again that parametric?
No, I haven't explained parametric yet. I just gave an example. This type of
Example.
equations are called parametric equation, where x and y are functions of a single variable t. Okay,
Okay,
so
sir.
these three types of equations we are going to study. So we'll start with Cartesian. As I said, many of the tools are already known to us. Okay, we just need to summarize those in a systematic manner, and for any example we'll use that standard procedure. We'll derive the conclusions like we did here, and we will draw the curve. Fine, so let's get to this. So the first point that we are going to see here is the symmetry. Whenever any of the Cartesian curve is given to us, first of all, we will see the symmetry of it. What do we mean by symmetry is, if you draw a semicircle, say, like this. So we know that semicircle, whatever is on the left hand side here, that is on the right hand side. Okay. If you draw a complete circle, it is symmetric about all the axes, x-axis, y-axis, positive x, negative x-axis, negative y-axis. So what is the use of symmetry? Say if I want to draw a circle, okay, and I know what is its region in the first quadrant. So we know that the curve is symmetric, circle is symmetric about both the axes. So what I can do is I can simply take the reflection, this, and what we get is the complete circle. So how do you use a symmetry is, so you draw a curve in a particular region and just take the reflection because the curve is symmetric about that axis. So there are different criteria by which we can check whether a given curve is symmetric about x-axis or it is symmetric about y-axis or whatever. Okay. So the first one is, the curve is symmetric about x-axis if the power of y occurring in the equation, the power of y occurring in the equation are all even. So wherever the y will occur, it will have, uh, the power is going to be even. So then and then only I can say that the curve is symmetric about the x-axis. Remember, symmetric about x-axis, y even. Why? Let's try to prove it. Take one point here and one point here. If the coordinates are xy and the curve is symmetric about x-axis, then what has to be the coordinates here? What
X,
coordinates? X comma minus y. Okay. So y is going to satisfy the equation and minus y will also satisfy the equation. And this is possible if and only if the power of y is even. Okay. So there is a simple example given to you, x is equal to y square. So if we draw the curve will look like this. In 12th standard, you have seen this in parabola. Okay. Then the next, if the curve is symmetric about y axis, so power of x has to be even. Again, the proof I can talk in terms of the points. So take a point here, x comma y. If the curve is symmetric about y axis, this point over here also, whose coordinates are minus x comma y, these 2 points must satisfy the same equation if both of them need to be on the curve, and this is possible if and only if x is having an even power. So these two criteria are going to be used a lot, and how it can be used, say, I will just check in which quadrant or about which axis my curve is symmetric. So I'll draw the curve in the upper quadrant, and upper quadrant it looks like this way. And I have the conclusion that the curve is symmetric about x-axis. Then by symmetry, what I can do is I can take the reflection about x-axis and I'll get a curve like this. So this can be given. I don't have to take the conclusion everywhere. I just take the conclusions in the upper quadrants, and by symmetry, I'll draw the curve in the lower quadrant as well. This is how the symmetry is used. Okay, so two criteria we have seen. Both of them are very important. So if the curve is symmetric about x-axis, power of y even, curve symmetric about y-axis, then power of x is even. Now, let's go to the next one. The next one says that the curve is symmetric about the line y equal to x. So look, these criteria you don't need to remember if you understand it. Okay, so this is the line y equal to x. Take a point here, x comma y. What this point is going to be, what will be the coordinates here? The curve is symmetric about this line, then no one. What the coordinates that x comma y will be if I take the reflection about the line y equal to x? Okay, for better understanding, what I will do is I will take it on the x-axis. I will take the point 1 comma 0. What will be the reflection about this line y equal to x? To take the reflection, what point you will get?
0, 1.
Exactly. 0 comma 1. So what this point is going to be?
Y, x.
Y comma x. Okay. So by interchanging x and y, the equation remains unchanged. Then we say that the curve is symmetric about the line y equal to x. Okay. So there is one example given to you. So if you replace x by y and y by x, you get the same equation. Then the curve is symmetric about the y-axis. Next. The curve is symmetric in opposite quadrants. What do you mean by opposite quadrants? Is the symmetricity about the origin. Like I will draw one curve over here. Curve is like this. So if you see whatever is going on in the first quadrant, the same thing is going on in the third quadrant. So the curve is symmetric about this origin. Okay. So if something is happening here, you'll get the same thing over here. So in this type of cases, what do we say is the curve is symmetric in the opposite quadrant. And if I take any point over here xy, we know that its reflection in the third quadrant is going to be minus x comma minus y. And what the criteria says is the curve is symmetric in opposite quadrants or about the origin if x is replaced by minus x, y is replaced by minus y. The equation remains unchanged. Do you have any question here? If it is there, then feel very good if you ask something over here. No questions? So I will ask you a question then. Does symmetric about origin is same as symmetric about both x's? Yes, anyone?
Yes, sir.
No, sir.
No, sir.
No. Why no?
So because in this curve it is not symmetric about we cannot say it is symmetric about y-axis.
Yes. So can I say ask other way around? If it is symmetric about both x's, then it is symmetric about origin. If it is symmetric about both x's, then it is
Yes, sir.
symmetric about the origin.
Yes,
So
sir.
other way
Yes,
around is true. If the symmetric about both x's, then it will be symmetric about the origin. But symmetric about origin may not be symmetric about both x's. Okay, so these are the criteria. So first thing we have seen, that is, so the equation is given to us. So first thing we are going to check is symmetry. I will write down the symmetry, whichever axis or the line, whichever according to which it is symmetric, we will write it down. Then the second point that we need to check is the origin. Does the curve pass through origin or not? Okay, so the curve passes through origin if there is no constant term in the equation, right? That is one criteria. We won't, I mean, good students can remember it. If not, then what we can do is the idea is put x is equal to 0, one variable 0, put one variable 0. If we get other variable as 0, other variable as 0, then the curve passes through origin. Okay, that is one criteria, and the other one is that constant term is not there. Any of the criteria will help. And this is, I guess, easier one, doesn't require a lot of remembering, and this is logical, so you don't need to remember this. So next one, if the curve passes through the origin, the tangent at the origin are obtained by equating the lowest degree term in x and y to 0. Look, this is a very important point. Almost in every example, this is going to be there. And this simplifies our calculations a lot. How does it simplify? Say for an example, I'll take an equation a square y square is equal to x square a square minus x square. Let's see whether it passed through origin. Okay. Example. Put x equal to 0. Put x equal to 0. So what we get is square y square is equal to 0, which means that y is equal to 0. So curve passes through origin. Curve passes through origin. Now the next question is, whatever point of intersection you get, maybe on x-axis, maybe on y-axis or the origin, we draw the tangents at that point to get the idea how does the curve intersect that point. Okay, and for that purpose, what we do is logically from our 12th standard studies, what we do is we take the derivative of this equation. What will be the derivative here? A square 2y divided by dx. What will be the right hand side here? So that will be 2 a square x minus 4x cube, right? So dy by dx is equal to 2 a square x minus 4x cube upon 2 a square y. What can you say at 0, 0? What can you say at 0, 0? No way.
Not defined.
So this turns out to be 0 by 0. This is not defined. Okay, and this will happen in almost all the examples. So whenever your curve passes through origin, talking about the nature of tangent will be quite difficult by derivative. So this is the alternative way, and this is a very strong result which says that the tangents at the origins are obtained by, and this is not just telling about the tangent whether it is parallel to x-axis or it is parallel to y-axis. It is actually giving you the equation of the tangent. So tangents at the origin are obtained by equating lowest degree terms to 0. What are the lowest degree terms in this? I'll rub this derivative part. I'll simplify the equation in order to get the lowest degree term. So a square y square is equal to a square x square minus x raised to 4. What is the lowest degree of a variable in this? The degree is 2, y square and x square. So what I will do is x raised to 4 is equal to a square in bracket x square minus y square. So this is the lowest degree term, not just one term. It is saying that equating lowest degree terms, all the terms in an equation you have to take and equate it to 0. So this is the lowest degree term. So x square minus y square equal to 0, which means that x is equal to plus minus y. So this tells me that there are two tangents at the origin. One is x is equal to y, the line x equal to y, and the other one is x equal to minus y. Is there anyone who is having problem in this? I hope I have made very much clear. It's very important. Remember it. Tangent at origin is given by equating the terms of lowest degree to 0. Fine. So there are types. If there are two or more tangents at origin, it is called a node, a cusp, or an isolated point. If the tangent at this point are real and distinct, real and coincident, or respectively. Okay, so there are different types. Okay, so we'll see it in the next slide. Go to the next page. Okay, so they are directly going to the. So I'll give you an example over here. Okay, so the third point here says that, so I will draw two types of curves. One is like this. So you can see that in both the curves, the curve is passing through origin. In the first one, if you take the upper branch of this curve, okay, for the upper branch of this curve, which is the tangent, x-axis or y-axis? Yes, which is the tangent?
X-axis.
X-axis. So if you take the lower branch of the curve,
Again x-axis.
again x-axis. So x-axis is the tangent twice. This is twice a tangent to the curve. Okay. So there are two tangents to this curve, and both of them are x-axis. So this is the first definition. Tangent at this point are real and coincident. If real and coincident, then the point origin is called the cusp. In this case, for this branch of your curve, the tangent is the line y equal to x. And if you take this branch of your curve, here you will have the tangent y equal to minus x. Let me tell you, this is the graph of this equation. Okay, so if you trust this equation, you are going to get this. So there are two tangents to this curve at the origin. So at the origin, if two tangents are real and distinct, then what it is called? Node. So these are just tangents are not called the node. That point is called the node where you get real and distinct tangents. At this, in this case, this origin is going to be cusp because the tangents at origin are real and coincident. In this case, the origin is node because the tangents at the origin are real and distinct. Fine. Go to the next point. Points of intersection. So in some cases, your curve may pass through origin. In some cases, it may not pass through origin. So once it doesn't pass through origin, what we talk about is whether it intersects x-axis or it intersects y-axis. So the point of intersection of curve with x and y axis are obtained by putting y equal to 0 and x equal to 0. This is combined statement, so it may not be very well understood at the first reading. So I'll take an example here. The example is say 3a y square is equal to x in bracket x minus a whole square. So if I want to check whether the curve intersects x-axis, intersection with x-axis. How do you check? What happens when a curve intersects y-axis? It will satisfy y equal to 0. Okay, so if I want to check whether a curve intersects x-axis, on x-axis, we know that all the points have y equal to 0. So I'll put y equal to 0. What do you get? 0 is equal to x into x minus a square. So x is equal to 0 or x equal to a. Right? So the curve intersects x-axis. Similarly, for y-axis, what I will have to put? I will have to put x equal to 0. If you put x equal to 0, what do you get? 3ay square is equal to 0. What do you get? Y equal to 0. So the curve intersects x-axis at the point 0, 0 and a, 0. And on y-axis, there is just one point which is 0, 0. Am I right? Any difficulty up to this? Everything clear? Again, this point. Tangent at the point of intersection is obtained by, let's not use this idea. We'll use our 12th standard way. If whatever intersection that you get, you find the derivative. So find derivative, find the derivative, and put the intercept. That will give you nature of tangent. That will give you the nature of tangent. Nature of tangent. Of course, this is also a good way by shifting the origin, but again, you will have to transform the equation. You will have to take x minus h, y minus k, change the origin, then think of it. But this will solve almost all of your examples. Okay. So whenever we need to talk about the tangents at some other point than origin, we'll go by our 12th standard way. We'll find out the derivative, put the point, and see whether it becomes 0 or it becomes infinity. And accordingly, we'll draw the tangent. Next. So just like I said in the previous one, cusp and nodes are explained here. This is already explained, so I'll go to the next slide. Asymptotes. Again, a very important point. What do you mean by an asymptote? The first example that we saw was like this. Okay, what was happening at infinity? So if you look at infinity, tangent to this curve was x-axis. Alright, so I can call this x-axis tangent at infinity. Okay, so as x tends to infinity, we get y constant, y equal to 0. So this was the asymptote. Okay, so whatever tangent to the curve you get at infinity, that is called the asymptote. And there are two types, actually three types of asymptotes, but in the syllabus we are going to study two types of asymptote: the parallel to x-axis, the asymptotes parallel to y-axis. How do you get an asymptote which is parallel to x-axis? By equating the coefficient of highest degree terms of x to 0. Remember, coefficient you are equating, not the highest degree term. So you look at the highest power of x, whatever is the coefficient of it, you equate it to 0, then you will get the asymptote parallel to x-axis. Then if I want to look at the asymptote parallel to y-axis, then we need to equate coefficient of highest degree term of y, coefficient of highest degree term of y to 0. Let's quickly see one or two examples here. So y square x minus a is equal to x square 2a minus a. What I need to check is asymptote. How do we check the asymptote? We'll check for the x-axis first of all. How do you check coefficients of highest degree term of x to 0? What is the highest degree of x? So this will be x into y square minus y square a is equal to 2a x square minus x cube. What is the highest power of x? Which is 3. What is the coefficient of it? 1 equal to 0. Coefficient is 1, right? I'll equate it to 0. Is it possible? No, not possible. So no asymptote parallel to x-axis. Asymptote parallel to x-axis. What about the asymptote parallel to y-axis? Look at the highest power of y. What is the highest power of y? 2. What is the coefficient of y square? X minus a. So I will equate x minus a to 0. What do you get? X is equal to a. This is the asymptote parallel to y. So this is how we are going to check. Again, a very important point. Please remember this. So to check the asymptote parallel to x-axis, equate the highest power of coefficient of highest power of x to 0. In order to get the asymptote parallel to y-axis, equate the coefficients of highest power of y to 0. Next. The region of presence, in some textbooks you will find this as region of absence.
Sir, can you take the previous slide?
Okay. Can I go ahead, Sumit?
Yes, sir.
So in some books, you may find this as a region of absence too. Okay. So what do we see is just like in that example, we had this type of curve. The value of y was 1, and we found out that for any value of y for any value of x, you won't get value of y greater than 1, or you won't get anything below this x-axis. So these were the region of absence. Region of absence. And this is the region where curve is present. So that is the region of presence. So how do you evaluate that, or how do you find it? The region is obtained by expressing one variable in terms of other, and then finding value of x at which y becomes imaginary. Okay, the curve does not exist in that region, it lies between these values of x. So just for understanding purpose, let's take one example. Okay, this is good. So y square a square minus x square is equal to a cube x. Okay, so this is the standard idea that we'll be using in almost all the examples. I'll write down y square as a cube x upon a square minus x square. Okay, so whichever variable you can do it. I mean, y square is, this term is always going to be positive. Remember that. That's why I'm taking y square equal to. Now let's just take x less than 0. What will happen? Okay, let me just factorize the denominator first. So this is going to be a cube outside x upon a plus x, a minus x, right? So if we draw the real line, a plus x, a minus x, so x, a is somewhere here. So if there is x less than 0, and here it is minus a, so x less than minus a, let's see what happens. If x is less than minus a, then this term will be negative, the numerator. What will happen to a plus x? What will happen to this? This will be less than 0 or greater than 0?
So less than 0.
Less than 0. Sure? Yes.
Yes, sir.
What will happen to a minus x?
It will be positive.
This will become greater than 0. And the total term, x is less than minus a. So what about this total term? What can you say? This will be positive or negative? With this conclusions, x upon a plus x, a minus x. This will be greater than 0 or less than 0. This will be greater than 0 because this is negative and this is negative. Two terms are negative, so minus will get cancelled out. This is already positive. So this total term is greater than 0. This is possible, right? So in this region where x is less than minus a, your curve exists. Okay. Similarly, I can make another interval now. For x less than minus a, my curve is existing. So now I will take an x which is between minus a and 0, or 0 to a, say for an example. 0 less than x is less than a. Then what happens? X is greater than 0. What about a plus x? A plus x is also greater than 0. What about a minus x? Is it greater than 0? Yes.
Positive.
So combining this, again curve exists. Now finally, what if x is greater than a? So x will of course be greater than 0. A plus x will of course be greater than 0. But what about a minus x? This will become
Like
less than 0. So in this case, this bracketed term is going to become, so if we combine this 3, what do we get is x upon a plus x, a minus x. This turns out to be less than 0. But this is equal to y square. A square term can never be negative. So your curve does not exist here. Curve does not exist in this region. In the similar manner, we will have to do it for all the examples. Like clear? If you have any difficulty, you can ask, or else we'll stop after summarizing things that we have done today. No problem. So tomorrow we just will solve the example and end this Cartesian curves tomorrow. There is this example. Examples we won't do it from the slide. It is not that interesting. We will solve it actually just like we do it in the class. Fine. Let's just summarize everything now. Once the curve is equation is given to us, equation is given. First thing that we need to check is methodology. You write it down. This is very important. First of all, check the symmetry about x-axis, y-axis, y equal to x, or the origin. Any two will help, or single will also help. After we check the symmetry, what we saw? Points of intersection. The points of intersection, whether it pass through origin or x-intercept, y-intercept. Once we see all of these, then we will talk about the tangent. Tangent A at origin. How do we look at this? Equating highest, lowest power terms to 0. Terms to 0. Once we do this, we'll get the tangent at origin, and at intercepts, which are non-origin points, by derivative. By derivative. After this, what we saw is fourth one. We look at the asymptotes. Asymptotes are nothing but the tangents at infinity. So we look at asymptote parallel to x-axis or asymptote parallel to y-axis. If we want to look at the asymptote parallel to x-axis, highest coefficient of highest power of x to 0, coefficient of highest power of x to 0 for asymptote parallel to y-axis, coefficient of highest power of y to 0. And the last one, region of absence. How do we check the region of absence? We write down the given equation as y square is equal to the function of x, or we'll write x square as the function of y, and accordingly we'll check for which value of x this term becomes negative, for which value of y this term becomes negative. This is the complete summary of tracing any of the given Cartesian equation. So that's all for today.